This video reconstructs the diagenetic history of two samples from a Welsh Carboniferous oolite over their 350-million-year-old existence. It demonstrates how much information can be revealed from thin sections using just plain light microscopy, both before and after treatment with the alizarin red S potassium ferricyanide stain, and observations using a cold cathode luminoscope. One sample comes from the Baltic quarry and one from the Blaenau quarry, north and northeast of Merthyr Tydfil. The oolite described is the Pulthicum oolite, assigned in 2013 by Waters and others to the early Carboniferous Corsaean stage. Its top was infiltrated by fresh water. It is overlain by a calcrete at the base of the Pantidaran Formation. Its geological setting has been described by Raven, 1983, Searle, 1986, and Wright, also 1986. The first sample comes from the Baltic quarry, where the Pulthicum Formation is 8 meters thick. The sample's position at the middle of the formation is shown by a red arrow against the column on the right. This image of the first Baltic thin section shows it to be a skeletal ooid grainstone. Its ooids, crinoids, and bivalve skeletons with rounded margins were formed under episodic, highly turbulent conditions, while a crinoid and fenestrate bryozoa were derived from a quiet water environment. For the crinoid's axial canal and the bryozoa's zooecial cavities are filled with lime mud. By the red asterisks. A group of ooids from this section is enlarged next. The lower central ooid, with an articulated ostracord as a nucleus, has a cortex composed of radial fibrous crystals crossed by faint concentric lines, clusters of radially distributed micrite crystals, and irregular patches of a later micrite that cross-cuts the earlier micrite. The later micrite is more abundant in adjacent ooids, and in some completely obscures their radial fibrous crystals. The intergranular pores between the ooids are filled with 2 generations of calcite cement. On the cross-polars image, the early fringe of 10-micron-sized crystals is labeled A, and the later cement composed of 100-micron-sized crystals is labeled B. A bulge at the base of the left ooid, by the red asterisk, is composed of 2 calcite crystals. This odd feature is more extensively developed in 2 ooids from this section, enlarged next. These moth-eaten looking ooids with irregularly shaped cavities are found side by side with ooids that have no cavities. The smaller cavities in the ooid's outer cortex do not distort its fabric, while larger cavities have expanded away from the ooid's centers, giving the grains an exploded look. They formed by a combination of dissolution, then fracturing. All the cavities contain only cement B crystals. The cross-polars images show how some single cement B crystals can be traced from an intergranular pore through the ooid's fractured margin into cavities within the ooid's cortex. A sequence of events that could account for these features is: first, calcite cement A precipitated on the ooid's surfaces and grew into the intergranular pores. It is possible the cavities opened before or during cement A precipitation, providing they were not connected to the intergranular pores where cement B precipitated. Second, the larger ooid cavities succumbed to fracturing, breaking both the cortex rims and their fringing cement A crystals. Third and last, cement B crystals nucleated at points tens of microns apart on all pore surfaces and grew to fill all pores. While these ooids were being altered, what was happening to the bivalves? The bivalve, running diagonally across the center of this image, is composed of two layers. One formed of prismatic calcite crystals and one of granular calcite crystals that are secondary after aragonite. The granular calcite has an irregular outer coating of micrite. The prismatic calcite layer has none. The intergranular cement A crystals, as they grew away from micrite, developed a druzy fabric, while, as they grew away from the bivalve's prismatic layer, developed a columnar fabric. Cement A's fabric is controlled by the orientation and size of the crystals on which it seeds. Cement B follows cement A and completes the filling of all pores. Now, the magic that staining brings to this thin section. The bivalve's prismatic layer and the ostrogod valve stain pink. Cement A, growing from the outer surface of the bivalve's calcite crystals into intergranular pores, is divided by the stain into three increments. The first, irregularly shaped increment stains pink. The second, that envelops the first, stains deep blue. An example is shown by the white arrow. The third increment stains pink. Cement B stains pale blue with irregular pale pink patches. The second and third cement A increments are also present in the bivalve's granular calcite crystals. The second increment occurs on both outer edges of the granular layer. The third increment occurs towards the layer's center, and patches of cement B occur at its center. The growth directions of these cement increments is shown by the black arrows, which is compatible with cement growing into a mold. At the top of this image, the bivalve's micrite and calcite layers come closer together, for after the original aragonite layer had dissolved, these layers, being unsupported, collapsed towards one another, accompanied by localized fracturing. A cathodoluminescence image of the same area shows the same features as the stained image, but they are better defined and some additional features are shown. The area around the center of this image is enlarged and interpreted next. The different cathodoluminescence areas are traced to produce a simplified sketch. The bivalve's prismatic calcite crystals are coloured light brown, with irregular yellow patches that cross crystal boundaries, likely due to recrystallization. The first cement A increment, labelled A1 and coloured dull yellow, occurs on the outer surface of the bivalve's prismatic calcite layer, but not on its inner surface, because when it precipitated, its aragonite was still present. After aragonite dissolved, the prismatic layer fractured, and the second cement A increment, coloured brown, precipitated on the shell's fractured surfaces by the white arrows. The third cement A increment is coloured yellow, and cement B is coloured grey. The other important skeleton in the Blaenau sediment, with a complex diagenetic history, are the crinoids. Crinoid 1 in section 3, when separated from its skeleton, developed a micrite coating that was then abraded and partly stripped, exposing a small area of the ossicle surface. Internally, crinoid 1 has uniformly scattered inclusions, and its skeleton, the stereome, is unrecognizable. Crinoid 2 has larger inclusions arranged in a rectangular grid that are remnants of its original galleried stereome. The structure of the bivalve on the left is difficult to resolve on this plain light image. Ooid 1 is microtized. Ooid 2, although partly microtized, still shows its radial fibrous crystals and a dissolution cavity in its outer cortex on the right. Cement A's crystals have final euhedral surfaces that are overlain by cement B crystals, well shown in the upper central intergranular pore. The cross-polars image shows the bivalve's calcite crystals and their attached intergranular cement have the same birefringence colours. Similarly, crinoid 1 and its attached intergranular cement crystal have the same birefringence colour, because their cements are epitaxially attached to their substrates. The various components of this rock, differentiated on this CL image, are used to produce a series of sketches showing its diagenetic development. The first sketch shows the grains at deposition. Well, not exactly. Their positions were traced from the thin section, but they moved slightly after aragonite was dissolved. Aragonite-coloured pale yellow is present at this stage as a bivalve layer. The first increment of cement A, coloured deep yellow, precipitated as a crystal attached to crinoid 1. Its zigzag shape shown here is an assumption. The first increment's crystals thought to occur on the bivalve's calcite layer, on micrite pore walls, and in pores between crinoid stereome are not shown here, as they were later modified or dissolved away. The bivalve's aragonite layer and part of its calcite layer are dissolved. Crinoid 2 compacted into the space in the bivalve shell created by this dissolution. The zigzag surface that was present on crinoid 1's epitaxial crystal is now ragged. The pore water, now supersaturated and reducing, precipitated the second Faroan cement increment of cement A that encapsulated any remaining increment 1 crystals and precipitated directly on exposed primary and secondary pore wall crystals. Increment 3, coloured orange, continued the growth of increment 2 with changes in composition and crystallographic habit. Increment 3 also filled cracks between some of bivalve's calcite crystals, probably caused by crinoid 2 compacting into the hole in the bivalve shell left after its partial dissolution. Cement B that fills the remaining pores is divided into 2 segments. The first is shown here, coloured mauve. The cement B crystal by the red asterisk was initiated at several isolated sites on different cement A crystals. The multiple initiation of this crystal is a puzzle. Cement B's second segment, shown here in purple, completes filling of the pores. Thin section 4 is included as it contains the largest intergranular pore of any from the 4 Baltic sections by the red asterisk. This pore was fully cemented before cement A stopped growing. No cement B is present, so the width of cement A is greatest here than in any other Baltic intergranular pore. The cross-polars image emphasizes a series of homoaxial columnar crystals centered on the bivalve's prismatic crystals. Cement A epitaxially attached to these crystals, growing away from the prismatic crystals in opposite directions. The cathodoluminescence image shows numbered increments of cement A. Increment 1 extends the bivalve's crystals into primary intergranular pore space. Increment 2 follows increment 1 and seeds directly on the opposite side of the prismatic crystals and grows into the bivalve's moldic pore. Cement A increment 3 has well-defined euhedral growth zones that can be traced throughout the intergranular pores. These zones are interpreted as synchronous. 2 prominent zones are used to subdivide this increment into 3. Using this CL image, the digenetic history of thin section 4 is now reconstructed. The position of these grains are those shortly after deposition, while they were still based in seawater. The lower bivalve has all its layers intact. The upper bivalve has no micrite layer on its upper surface, perhaps due to the loss of a calcite layer shortly before deposition. Precipitation of cement A's first increment occurred on all pore walls. Larger crystals grew on the bivalve's calcite crystals, and smaller crystals on micrite forming the pore walls, shown figuratively here by yellow dots. The pore water now became undersaturated with respect to aragonite, so the bivalve's aragonite layers were completely dissolved. Their micrite coatings were not dissolved. They still preserve the position of one side of the shell's margin. Cement A's first increment on the outer surface of the bivalve's calcite layer was modified, and that on the micrite pore walls was removed. Cement A's second increment seeded directly on all pore wall crystals, enclosing any surviving increment 1 crystals. Cement A's third increment shows well-defined mantle zones that are used to subdivide increment A into 3A, 3B and 3C. Only 3A is shown on this sketch. The distribution of 3B is now added. Its growth rate varies between pores. The larger pore, labelled 1, has wider 3B crystals than in the smaller pore, labelled 2. Cement 3C completes the filling of thin section 4's pores. The petrographic relationships from all 4 Baltic images are now used to reconstruct the diagenetic events that have affected the Baltic sediment. In modern Bahamian ooids, the appearance of tangentially oriented aragonite crystals are preceded by a series of precursor phases. Diacenebolite 2019. Whether similar events preceded the Baltic's radially oriented calcite crystals is not indicated by the petrographic information described here. The distribution of micrite-filled endolithic borings in modern ooids, while still in the marine realm, described by Thielert and others in 2024, can be matched with that in the Baltic ooids. This indicates the Baltic ooids have not changed at the scale of this examination since leaving their marine environment. The cathodoluminescence image of the Baltic's radial fibrous crystals on the lower left indicates they recrystallized. However, when this happened and what effect it had on the composition of the products is not revealed here. When crinoid ossicles separate from their skeletons, the volume of each ossicle is half stereome and half pore space. As ancient crinoid ossicles keep their original shape and volume, and their magnesium calcite stereome stabilizes with little volume expansion, this means approximately half the volume of ancient crinoid ossicles are repositories of introduced material. The magnesium calcite stereome of Carboniferous crinoids, Dixon 2001, either stabilize internally when their shape is preserved, or their stereome's breakdown products mix with externally sourced material and their stereome shape is lost. The stereome of crinoid 1 from the Baltic sample is unrecognizable, although its breakdown has probably contributed magnesium for the formation of micron-sized dolomite crystals within its ossicle. Crinoid 2 has a poorly preserved patch of stereome. The space between the stereome is filled with cement. The bivalve structure on the right image is difficult to see in plain light, but is well defined on the CL image. Its 4 calcite layers are given a yellow overlay, and the aragonite layer is given a green overlay. The 4 calcite layers have bright and dull orange luminescent patches that do not cross the layer's boundaries, indicating this pattern was generated internally. There is no petrographic evidence to indicate when this stabilization took place relative to the changes that occurred in the intergranular pores. In contrast, the aragonite layer that was dissolved to form a mold was filled with a sequence of cements that precipitated both inside and outside the mold, linking events within the bivalve to those affecting the intergranular pores. The first cement A increment, labelled A1, was either dissolved or is present as altered remnants of its former crystals. As cement A is the first cement to precipitate, it probably was marine magnesium calcite, its instability leading to its modification. This modification may well have been assisted by its marine pore water becoming undersaturated due to oxidation of organic matter, a widely distributed event in marine sediments, according to Saunders, 2003, and Wright and Churns, 2007. The second cement A increment was precipitated from pore water that had become supersaturated with respect to calcite and reducing, as indicated by its Ferroan stain. The third cement A increment continued the second euhedral growth with a change in crystallographic habit from acute rhombohedron to less acute scalenohedron. Such a form change has been produced experimentally on calcite, with a rise in temperature from 12 degrees Celsius to greater than 30 degrees Celsius. Coltle and others, 2024. Such a rise in temperature is expected for the Baltic sample, as it became buried under an increasing pile of sediment. During early cementation, the rate of cement growth is linked to the size of the crystals on which it seeds. Slowest on micrite, fastest on crinoids. In section 1, between ooids with micrite walls, cement A only fills about 10% of its intergranular pores, whereas in the second and third sections, with larger crystals in its pore walls, it fills about half the intergranular pores. This difference of cement growth rate can lead to oolites with a striped cementation pattern, as their episodic deposition leads to alternating skeletal, strongly cemented, and ooidal, weakly cemented layers. During late cementation, however, the rate of cement growth varies between pores of different size. On image 3, cement A3B is twice as wide in the largest pore than in the smallest pore, shown by the length of the black arrows. As pores become cemented, smaller pores lose their connectivity before larger pores, reducing carbonate supply and cement's growth rate. After cement A had precipitated, the larger cortex cavities in section 1's ooids were fractured, before cement B precipitated and healed these fractures. Cement B's randomly oriented crystals were initiated tens of microns apart on cement A's final euhedral surface. The lack of connection between the two cements was probably due to a pause in precipitation when cement A's surface aged. The growth of cements A and B were different. Cement A's internal growth surfaces are simple euhedral surfaces from which its crystallographic habit is readily determined, while cement B has complex internal surfaces whose growth habit could not be determined from the images available. Precipitation of these two cements differed kinetically, After precipitation of cement B, its crystals were cut by polysynthetic twin planes that offset its growth zones. Raven recognized these in 1983 as structural twins, linking them to the nearby late Carboniferous gneiss disturbance. The Pulthicum Formation near Clydach, kilometers east of Blaenau Quarry, has been entirely dolomitized. Raven 1983. And the exposure of the lower Carboniferous formations around the quarries where the samples were taken have been rained on over the past few thousand years, which has resulted in the deepest cave system in Britain forming beneath ground. Neither of these two events have left any identifiable changes to the petrography of the two samples described here. They have remained in stasis for 300 million years. Switching now to the second sample, taken a few millimeters below the top of the Pulthicum oolite at Blaenau Quarry. Like the Baltic sample, it is a skeletal ooid grainstone. Its thin section shows a mix of rounded grains, bivalve shells, brachiopods, gastropods, and dasycladacean algae. This section is correctly oriented. The large curved shells by the red asterisks, sheltered areas beneath them from the rain of small grains that occurred during deposition. The boxed area, upper left, is now enlarged for closer examination. Wow! The round grains are interpreted to have been ooids whose cortices have been lost. Ooid 1 resembles the Baltic ooids. Ooid 2 has a cortex made of granular crystals, and those labelled 3 have cortices made mainly of single calcite crystals. A group of type 3 ooids in the boxed area is now described in detail. The three bodies labelled 1, 2, and 3 were ooids, but have had their cortices completely dissolved, resulting in oomoles, which were then filled by 3 different solids. The first was calcite cement crystals that grew from the oomole's walls a few microns towards their centers. Their terminal euhedral surfaces were then made irregular by dissolution. The second is a sediment of transparent and opaque crystals a few microns in size that occur around crinoid in Oocast 1. Similar sediment was interpreted by Raven in 1983 and Searle in 1986 to be sediment swept into South Wales lower Carboniferous oolites during episodes of subaerial exposure. The third consists of 1 or a few calcite crystals, several hundreds of microns in size, that fill the remaining space at the center of the oomoles. At deposition, ooids rest on one another at point contacts, but the margins of these 3 numbered grains overlap one another, indicating minor compaction occurred before their cortices were dissolved. This dissolution only affected the ooid cortices. It did not affect some ooids' skeletal nuclei or their surrounding calcite cement that preserves the ooid's shapes. The cross-polars image emphasizes the polysynthetic twin planes that cross the large cement crystal and crinoid 1's nucleus. The crystal filling the center of oomold 2 extends into oomold 3 by the white arrow, indicating when this crystal grew, no barrier existed between the two oomolds. Now the stained image. The distribution of the dark internal sediment in the oocasts is accentuated by the etching caused by the acidic stain. The large calcite crystal filling the center of oocasts 1 and 2 are stained blue with angular pink patches, a pattern that matches cement B crystals from the Baltic thin sections. Most of the intergranular cement has a blotchy pink and blue stain, but the early cement on the lower left with the blotchy stain is separated by its euhedral surfaces from a later unstained cement at the center of the intergranular pore. This image is of a second group of oocasts from the same Blainoni thin section. The lower oocast includes an echinoderm spine, thought to have been its central nucleus, but after cortex dissolution, it lost its support and fell to the oomold's floor. The left oocast contains an eccentrically placed ostracod valve. The upper central oocast shows no nucleus. The first cement to precipitate in its oomold did so mostly against its right side. The leading edge of this cement cuts smoothly across several crystals and is interpreted as a dissolution surface. Under cross-polars, the stereome of the echinoderm spine in the lower oocast has the same dark blue birefringence color as the surrounding cement crystal, indicating the cement crystal seeded on the echinoderm stereome. The CL image shows different oomolds were filled by different cements. The last cement to fill most of the lower and upper right oocasts is non-luminescent with orange luminescent hairline euhedral zones. The expanding pattern of these hairline zones indicates the crystal's point of appearance on the spine's surface and the way it expanded to fill its oomold. The last cement crystal to fill the three oocasts on the upper left have complex, dull and bright orange luminescent zones, like those described for the late cement B from the Baltic thin sections. The intergranular cement is divided into two. The early cement has a non-luminescent orange and yellow spotty pattern. The later cement is non-luminescent with hairline orange luminescent zones, like that in the lower oocast. A sequence of events is now suggested for the formation of these oocasts. 1. Minor interpenetration of some oomolds occurred. 2. Precipitation of the early intergranular cement. 3. The ooid cortices were totally dissolved. Their undissolved nuclei moved to the oomold's margins. 4. Orange luminescent cement grew from the oomold's margins, probably with euhedral surfaces. 5. These euhedral surfaces were dissolved. 6. Sediment was washed into some oomolds. 7. Non-luminescent cement with orange hairline luminescent zones grew into some oomolds, and completed the filling of some intergranular pores. 8. The few oomolds that remained open were filled with the dull and bright orange luminescent sector-zoned cement B. Returning now to the lower magnification image of the blind on eye thin section that is now stained, the larger calcite cement crystals filling the bivalve's molds and larger intergranular pores are differently stained depending on the crystal's orientation. Those with their C-axes parallel to the section's surface stain pink. Those with their C-axes at right angles to the section's surface are colorless. Dixon, 2003. Brachiopods and crinoids stain pink. Most ooids stain purple, and the subvertical irregular fracture filled with Faroan calcite cement stains blue. The boxed area, lower right of this image, is now enlarged. Most of these ooids have cortices composed of blue-stained, equant, Faroan calcite crystals that surround centrally placed nuclei. The structure crossing the top right corner of this image used to be an aragonite bivalve shell with a micrite coating, but the original shell was completely dissolved to leave a mold. This mold and the intergranular pores are now filled with calcite cement. Both have the same blotchy pink and blue stain. A group of ooids from this section are now examined more closely. The ooid cortices are composed of equant, inclusion-rich crystals with irregular intercrystalline boundaries. The intergranular pores have radially arranged elongate calcite crystals against the ooid's surfaces that merge into fewer crystals tens of microns wide at the center of larger pores. The CL image shows the mosaic of crystals forming each cortex have a dark to light mottled brown luminescence pattern. Within some of these crystals are non-luminescent euhedral shapes, a few microns in size, with a yellow luminescent outer zone. These could mark the points where alteration of the cortex started or where they were later replaced. Now, some remarks summarizing the Pulthicum samples. Ooids, a few millimeters below the Pulthicum's top surface, are preserved in 3 different ways. A few are like the Baltic ooids, but about half have cortices composed of granular Faroan calcite crystals, and the other half are oocasts. These 2 dominant types occur in groups side by side in the blind eye thin section, suggesting fluid access was localized during their formation. The transformation of ooid cortices into granular crystals was carried out under reducing conditions and was initiated at multiple points in ooid cortices. Transformation of the original material was incomplete, for sufficient unaltered material was left behind to support any ooid nuclei in their original positions. In contrast, dissolution of ooid cortices resulting in oomolds was complete. Any ooid nuclei left after dissolution were unsupported and came to rest against the intergranular cement. The filling of these oomolds occurred during periods of alternating precipitation and dissolution. The granular and oocast preservation types that dominate the top Pulthicum sample do not occur in the middle Pulthicum sample. Not only are the preservation types different between the top and middle Pulthicum, but their intergranular cements are also different. The middle Pulthicum intergranular pores were filled with cements A and B. The earlier cement A is divided into 3 sharply defined increments. The top Pulthicum pores were filled with 2 poorly defined cements that have been recrystallized. They cannot be correlated with cement A from the middle Pulthicum. Cement B, due to its complex zonation, can be recognized in the top Pulthicum, but only as the latest filling of some oomolds. At deposition, the top and middle Pulthicum samples were similar skeletal ooid grainstones. They are now different because they evolved along different digenetic pathways. While the top and middle Pulthicum samples are different, the top Pulthicum has similarities with Pleistocene samples from the Vadose zone. Ooids with granular cortices are similar in both the top Pulthicum and Pleistocene Vadose oolites, despite their differences in original mineralogy. Ooids whose cortices were dissolved to form oomolds also occur in both locations. The Pulthicum oomolds, however, have been cemented to form oocasts, while those in the Pleistocene are unfilled. The occurrence of cement B in the Pulthicum oomolds is thought to have occurred during burial, an event yet to affect the Pleistocene deposits. While the Pulthicum and Pleistocene ooids are similar, their intergranular cements are different. Meniscus cement, illustrated here from the Jultus sample, was not recognized in the top Pulthicum sample. Its intergranular pores are filled with cement, but no curved surfaces that could have been air-water meniscus interfaces were found within this cement. The intergranular cement in the Corinth sample, image 4, has been dissolved. The top and middle Pulthicum intergranular cements show breaks in precipitation, but there is no evidence that any of these breaks were associated with dissolution. The top Pulthicum oomolds do, however, show episodes of dissolution affected their cements, but not the intergranular cement. Some final comments. The presence of growth surfaces within crystals, as shown here by staining and cathodoluminescence, together with standard petrographic microscopy, shows how a multitude of digenetic events can be interpreted from thin sections. This combination of techniques has been available for decades, but has rarely been fully utilized. New petrographic techniques have appeared since the 1970s that extend this study, and different techniques for instance isotope studies, are needed to substantiate some of the petrographic relationships described here, for they are often ambiguous. The two samples examined here give only a snapshot of the Pulthicum's subaerial exposure event. To properly document its environmental transitions and spatial distribution, as recorded in some Pleistocene examples, many more samples placed throughout the Pulthicum are needed.